So real quick, just a couple slides, and I'm going to turn it over to Michael because that's really what you care about. There we go. I'm going to get focused to the right thing. So one, I want to thank our sponsors. Oh, I will say I apologize for any noise in the background. The dog has decided he wants to hang out with me, and I know he's going to eventually leave. And so, of course, the kitchen's sitting right next to me. But yeah, I want to thank our sponsors. Starting off right now, Modus and Tech isn't really doing much, but they have been a part of Louisville.net for so long that I feel is worth it to keep on mentioning them. Normally, Modus would be providing our meeting space, and Tech Systems would be providing our food. And then Green Events Technology, which is my little company that pays for Zoom and all that great stuff. All right. So just some upcoming meetups. So I have not put this on Meetup yet, but I'll do that probably tomorrow. Next month, we're going to have Jay Harris, and he's going to talk about anxiety-free databases for .NET Core. Jay Harris is an amazing speaker. I highly recommend you come to that. And just a really good guy. There will not be a meetup on August 20th because that will be during Copalooza. Now, with that being said, maybe we'll do something special. I don't know. But at the moment, we definitely won't have a normal presentation type thing. I actually do have a speaker lined up for September 17th. And it's actually a pretty big name. But he has asked me not to mention anything until next week. And primary reason is it's a big enough name. He didn't want attention taken away on social media with Black Lives Matters and everything going on. So I'm fine about it. But I will say, if you do see Sharp, this guy's pretty important to you. And I'll just leave it at that. All right. Next week, you'll know what I mean by that. Right. So definitely look forward to that. Some other meetups coming up next Thursday. We have the Azure group. We'll be meeting, and we'll be learning about Azure notebooks, ways how you can write queries to have a notebook that allows you to keep like different queries you want to run and run directly from there. I need to get more into notebooks, the Juniper notebooks. So I'm really looking forward to this. Sarah is also a really good speaker, so that'll be a great presentation. Also check out, we have, if you're a tech leader, so whatever that means, right? I mean, that might mean like you're a director like myself, but maybe it means you're just leading a small team, right? You have special needs that you have part of the job, and that's what tech leaders is all about. Right now, we were meeting a couple times a month, but right now, because of the pandemic, we're only meeting the second Tuesday of the month at 8 o'clock in the morning as for our coffee and discussion. We've been doing that for about 2 years. And it's even with the pandemic, that's been going on really well. It's just a way, somewhere to go and listen to other tech leaders and kind of help help each other solve problems that we're having. There's also the Louisville IT Happy Hour, which is normally the evening of the second Tuesday of the month. And that's just a social event, right? And we actually, this month we did a little bit different. It was Tuesday. It was this Tuesday. It was great. We had I don't know, it was around 15 people, mostly Code Louisville students. Sure enough, if you don't know anything about Code Louisville, if you know anything about Code Louisville, it's a great program. Helps people, like David, who's been doing other stuff, trying to transfer over. But also a lot of people, like one of my favorite guys who's gotten out of Code Louisville, he was wait staff just 2 years ago. And now he's already a tech leader, right? Because he's moved up so quickly. Actually, I guess 3 years ago. But but the IT Happy Hour is not just meant for Code Louisville. Code Louisville, actually, students have a requirement to attend sessions, and so that's why you see a lot of heavy ones on that one. But some other things, to point out. And actually, this is bad because the one I'm going to say, so like there's groups all over the country, or all over the world, really, all right, that you can attend. Right. And that's the great part about the pandemic, right? We actually they're more available. Right. Now, funny part is normally Sean would actually be on here. He runs the Tulsa group. He's going to be joining a little bit late. He's stuck with something at work at the moment. But I've been attending those. I know Michael attends the Tulsa group. But yesterday, the day before, I was attending a group. So Southeast London, in the United Kingdom, right? I was actually, because a friend of mine was speaking, so I wanted to be there to support him. But it was number one. It was interesting to see, because again, it was folks from the London area, right? So you were getting a different aspect on the .NET world. There's a lot of other great groups, and I particularly put in groups that are more local. So Evansville is a couple hours away. They've moved online. Cincinnati has a whole lot of events that are online right now. Another interesting one, the Granite State. So they actually meet every night, and they're doing like a stand-up. And it's really whatever you're working on, you can kind of talk to other people, maybe get ideas from them. I have not attended one of those yet. I keep on saying I'm going to, but it looks really interesting. And then the last one here, the virtual user group, the .NET virtual user group. So that's run by the .NET Foundation, and it's actually groups that are in the .NET Foundation, which Global.NET is a .NET Foundation group, and we can actually be hosted by them, and it gets hosted on YouTube, right? And it's a great part, so you can see all kinds of different user groups that'll be hosted on there. We won't be doing that because right now we're live on Twitch, and as a Twitch affiliate, I am not allowed to do multiple streams. Right? I could do it if I'm not streaming on Twitch, right? But since I'm kind of trying to build a brand on Twitch, I will keep to their policies. All right, which sure enough, so. We were talking about this earlier before. I do Twitch every day. TaleLearCode is the channel name, and you can see what we're doing, right? So, like today, we were having an interview with Mike Umson, who will be a Copilot speaker, but is also a world-renowned designer for APIs. He does a lot of teaching about around designing APIs and such. Or otherwise, other days we're just writing code, right? And it's really cool doing that. I mean, number one, we're getting ideas from watching other people. But like for me, I talk when I code anyways. So it was kind of natural. But now I talk even more, right? But it helps me. It helps me process through things. So those are a lot of fun. So all right. So Copalooza, our annual software development our event. So if you have not heard of Copalooza yet, I'm a little bit biased, but I think it's a pretty cool event. And this year it'll be completely online for obvious reasons. Actually, it's not 100% true because we're going to have a command center downtown, but that will only be like 12 people that will be running everything. But so August 19th through 21st, the 19th is our workshop day. The cool part is, so normally we have different ticket levels and everything. Because we went online, it's just one ticket level. Unfortunately, it's still $150. I would love to have gotten cheaper, but honestly, it still costs a lot of money to run even an online event. Because I have to use a lot of technology and such. But you get access to all these things right for that price. Access to all the sessions, all the workshops, and recordings to most. I really do need to change that to most of the sessions and workshops. There are a couple that will not be available on recording. Because those folks do those presentations elsewhere, and they're allowed to do them live, but they're not allowed to have them recorded. But what they would say, it's like 2 or 3 that won't be available on there. Along with it, concept you can do at a conference, and we've done this a couple times, is open space. And so you can see all these great sessions on there, but maybe you want to talk about something that's a little bit more unique. Most likely, there's someone else at the conference who also would like to talk about that. And that's what open space is all about, right? So generally to put a name on a whiteboard, and then you meet at a certain time, all right? Or you don't put a name, you put a topic, I should say. And we're going to be able to do this online, right? So so that'll be a lot of fun. There will be networking. Basically, kind of think of like a speed dating thing, which sounds a little bit weird, but actually it's about the same thing as if you're just walking a hallway and all of a sudden you start talking to somebody, right? Same concept. Along with, we're still going to be able to have an expo hall with our sponsors. So you'll be able to talk to the sponsors. And then, one of the big things, I wanted this to be as real as possible. All right. We're still doing attendee t-shirts, and we'll be sending those out. Now, the big caveat is there, we have to have 500 paid attendees, which we should get to. But that's where the cost break, where we can afford to do the t-shirts. But like I said, I'm pretty confident we'll get to that number. So you can go to copalooza.com and you can sign up. Now, with that being said, as part of TaleLearCode, I am doing a giveaway of a ticket. So if you go to that bit.ly link, you'll see this page right here that I've snipped out here, which will provide you ways to enter in. Entries will be taken until 12:29 Eastern Time next Friday, and then around 12:30, so sometime between 12:31 on the 29th, I'll be spinning the wheel, and we'll be giving that ticket out on the stream. I would love for everyone to be on the stream, but you don't have to be on the stream to win. Right? I didn't realize I had an animation in there. But also, and I was talking about this, so as part of the stream, we are interviewing Copalooza speakers. This is the list as of right now. I do have some more signing up. Generally, these are on the Tuesdays and Thursdays, 11:30, but you see a couple of other dates and times. It was actually so awesome. We got so many who signed up real quick that I had to open up other times to do this. And these are a lot of fun, right? You look at the 4 we've done so far. You see, so Kevin Griffin. I mean, he's been an MVP for 10 years. So he's been around for a long time, speaking at a whole lot of events. Sean, who runs the Tulsa group, he's a little bit newer to speaking, right? And he's been around the community for a long time. He's a little bit newer, at full-time speaking. But like Johnny, this will be his first conference speaking at, right? So we've been having a lot of fun with or like Mike is like I said, he's a world-renowned speaker. It's all over the world. But, so lots of great people will be interviewing. I've been having a lot of fun doing these. And then they are available at that bit.ly link, or you can search for TaleLearCode on YouTube and you'll find them. So like I said, that's been a lot of fun. All right, so normally I have this slide, which to remind me to remember when we'll go to BJ's afterwards. We can't go to BJ's. Actually, they are open again, but obviously we're not going to leave our houses after this. But we do keep the line free afterwards. We turn off the Twitch, we turn off the recording, so you can say whatever you want to say. But it's a great way to keep the conversation going on afterwards. Admittedly, sometimes you can stay as long as you want. I mean, these have gone as long as 1 o'clock in the morning, right? So it's people definitely have a lot of fun on that. All right, so with that, I'm going to turn this over. Let me turn off my slides. Let me find. Oh, okay, it's all the way over here. I have 3 monitors, and apparently OBS, or not OBS, but Zoom decided to go all the way to the other screen, far monitor. And I'm going to turn it over to Michael Perry. Michael actually has spoken to Copalooza at least once. I can't remember if you've been there multiple times or not.
Just once, yes.
Okay. But so Michael comes from the Texas area. And actually, like I said, I think you'll really enjoy this talk. I mean, I have not seen this presentation yet, but I've been told it's really, really good. Of course, now I've set Michael up for that. Now I'm going to turn it over to Michael.
Yeah, thank you very much, Chad. And if you all love math as much as I do, then you're going to have a blast. If you don't love math as much as I do, well, then you're probably going to love math by the time you're done with this. That's my goal. I'm Michael Perry. I love to talk about the intersection between software and mathematics. I love to see how we can use math in order to make more reliable software. And as I'm researching and reading math papers and applying theorems, I came across this idea of ACID 2.0, and this is kind of the centerpiece of a whole set of mathematics that's all about making more reliable distributed systems using mathematics. So Using the principles of ACID 2.0, I'm able to design much better APIs, much better messaging systems than I could before I learned about this set of math. And so I put those things together, and I really want to share them with everybody else so that we can all build much more reliable systems. So when you see 2.0, that means different from the 1.0. Well, what was the 1.0 of ACID? So a lot of you might be familiar with ACID transactions of a relational database. You've got atomic, consistent, isolated, and durable. And these are 4 promises that the database makes to your application. So going through them real quick, it promises that the transaction is atomic. So if something happens, it'll roll back, or if you're finished with it and you commit it, it'll be completely committed. It won't be in some halfway state. The transaction is all or nothing. It's atomic. The second one, consistent. A little bit of a fuzzy definition, but this basically means the database is going to uphold the invariance of your application. Database invariants include things like uniqueness constraints. They include things like foreign key relationships, that when you're finished with this transaction, something that's supposed to be unique, there really is only one row that has that value. If there's a foreign key, then there really is a primary key in the reference table. But consistency also relates to whatever your application does. So it's application invariance. If you come from kind of a physics background, you can think of invariance as your conservation laws, like the conservation of mass or conservation of energy. They're things that are just going to be true as you move through a system. They don't change. They are invariant. As you move through a system. So in a financial system, for example, you might have a rule that says you can't create or destroy money. Money is conserved. So you have the same amount of money before and after the transaction. That would be a consistency rule. And so decrementing a balance from one account and incrementing the next one, commit your transaction, the database guarantees that it will be consistent. So that's what that consistency means there. Isolated. That means that if your application is using a database and another application or another thread within your application, or the same app just running on a different node, if you've got another transaction happening at the same time, you're not going to be able to see what's happening inside of that transaction until you both commit. So you're going to be isolated from one another. And then durable. This is the most important of the promises. Basically, it means once you've committed, those changes stick. They're not going to just disappear. So a database would be a pretty poor database if it wasn't durable. And so we've got these 4 promises that the database makes to us as application developers that then we can rely upon. And if you think about how you build an application, this seems like a necessary set of promises. It would be really difficult to think through how do you build an application that has multiple threads if you don't have the promise of isolation. How can you build a financial system if you don't have the promise of consistency? So these things are pretty important. And what they do is they make the database look as if you are the only application in the world. This thread is the only thread that's running. This request is the only thing that's happening. So it gives you that illusion that it's just your application, one thing, and the database. And that's the ACID transaction promises. So ACID transactions have been around for a long time. And for quite some time, it was sufficient that we had a whole bunch of terminals all accessing one central machine. And then the world started changing, and there was the web, and there were machines scaling out and different services talking to each other. And then we found that we needed to have data spread across multiple databases, but we still wanted ACID transactions. So we came up with this idea of having distributed transactions. And so if you think about what it takes to make a transaction distributed, you have to be atomic, consistent, isolated, durable for each transaction across two different databases or more different databases at the same time. And that can get kind of tricky if you really start to think through what does it mean for me to be talking to one database and then turn around and need to do an insert on another database. And people who are using those two databases, they need to be isolated from my changes. What does it mean for me to commit my transaction when it's happening in two different places? Is it written to one and then written to the other? What if it fails on the other? Does it roll back on the first? All of these problems are pretty tricky to solve. So in order to take the transaction ACID properties, that promise that the database gives us, and distribute that across multiple databases, that's a bit of a hard problem. Fortunately, we have really smart people working on that problem. One of them is Pat Helland. So he is one of the pioneers of distributed transactions and thinking through how to make ACID scale. And one of his achievements was at Microsoft. He helped build the Distributed Transaction Coordinator. So if you have any experience with the Distributed Transaction Coordinator, then you can probably keep your groaning to yourself. It does have its problems. It will bite you. But it was a very difficult thing to make work, and folks like Pat Helland really needed to dig into some serious math in order to try to figure out how to make it all come together. In his paper in 2009, Building on Quicksand, what he's talking about is how you build a reliable system upon the quicksand that is the network. You see, networks are not as reliable as we would like them to be. The latency of a network communication is not zero like a local call would be. Things are not guaranteed to succeed. These are all fallacies. If you look up the fallacies of distributed computing, you'll see a whole list of things that we assume are true, but are just not true when you've got a network in between. And so on that quicksand of the distributed system, Pat Helland was telling us exactly how he and his team built something as robust as a database transaction, how he provided the ACID properties over a distributed system. And so you can see here one of these diagrams. This is an actual illustration of the steps necessary in order to distribute a transaction across these three replicas. And it's not trivial. It's quite a lot of work. You can see that they're doing multiple writes over time, and then they are checkpointing that and saying, okay, we're going to treat that as a unit, and now we have to make sure that it's atomic from one unit to the next. And it gets really difficult. And so he was noticing in this paper, while telling us exactly how all of this magic is accomplished, he was noticing that maybe we don't actually need the ACID promises from our database. Maybe if we took something less, if we expected less of the database and instead expected more of our applications, we could flip that around. We could provide some promises that if our applications behaved in this way, then we could build on top of these systems as they already are and not have to build on top of quicksand. And so he documented what these properties are that our applications can uphold, and he called those ACID 2.0. So, of course, he called them ACID 2.0 because there are 4 of them, and they have the same acronyms. Well, that's not an accident, but in some sense, it's quite fortunate. Each one of these terms is actually a well-defined mathematical term. And so with these terms, he was able to prove that a distributed system is eventually consistent if it's just built on a very simple database and not requiring the ACID 1.0 promises. So let me go through these promises or these properties for you. So we've got the associative property. Now, if you are familiar with your algebra, then you might recognize that different algebraic operations are associative. So addition is associative. You can put the parentheses around any group of addends, and you will still get the same answer once you've added them all up. Similarly, addition is commutative. If you were to swap the order of two of the addends, you would still end up with the same result. And then you've got idempotent. This is a math term, but it's probably not one that you learned in algebra class. This means that if you were to do the same thing twice, you would still get the same answer as if you'd done it once. And then finally, we've got distributed. And this is talking about the property of getting the same answer no matter where you perform that operation in the system. So we've got these ACID 2.0 properties, and if our applications provide these properties, then we can build distributed systems and rely less upon the promises that our database or our networks try to provide. So let's dive into these in a little bit more detail. We can frame this in the form of the hard problems of distributed systems. And fortunately, there are only two. They are number 2, exactly once delivery. Number 1, guaranteed order of messages, and number 2, exactly once delivery. So if you've ever worked with a queuing system, then you probably have recognized that every once in a while, when you pull from the queue, you'll get a message that you've already received. That is a very difficult guarantee for the queuing system to give you. So it's a hard problem. You might notice that you've gotten the payment message out of the queue before you actually got the invoice. So it's like, oh, these arrived out of order. How am I supposed to handle those? That's a hard problem. But fortunately, we have solutions to these hard problems, and the solutions can be found in the ACID 2.0 properties. The first solution is the idempotent property. So if you were to take a look at an HTTP resource, so let's say I've got an API published on the web, and if I get from this URL /people/42, I might get back a resource with name Bob. Okay, so now I want to act upon that resource. I want to make changes to it. I can do that using the HTTP verb put. So I will put to people42 name Robert. And now what's the value of that resource? Name Robert. Excellent. What happens if I put people42 name Robert a second time? Well, you would expect it not to change. You would expect it to still be name Robert. And so that means that even if I perform that operation twice, I still get the same result as if I'd performed it once. So why is that important? Well, that's because it's very difficult to guarantee exactly once delivery. So if I might possibly repeat messages, then on the repeat of the message, if I can guarantee that I'm not going to change the system, then I can tolerate those repeated messages. I don't have to rely upon my queuing infrastructure to not repeat a message. So the HTTP verb put is guaranteed to be idempotent. There are a few other HTTP verbs that have that property. So there's patch and there's delete. But post is decidedly not idempotent. So if you were to post to a URL, it's intended to create a resource. You post again, it's going to create a second resource. And so posting twice is a noticeable difference from posting once. But put, idempotent. It's right there in the spec. So we've got idempotence in order to handle that exactly once delivery. Let's take a look at another one of the ACID 2.0 properties and see what else we can get out of it. So let's take a look at the commutative property. Let's suppose that I have an application that's a game. It's a word-finding game, like a Boggle or something like that. So I find a word and I say, okay, that one scores 3 points. So here's the score 3 points event. Now my total score is 3. Then I find another word, oh, that scores 5 points. Now my total score is 8. What would happen if I had received those messages out of order? Well, then I would have scored 5 points first, and then 3, and I would still have a total of 8. So I still get the same result, even though I've received the messages out of order. So my message handler is being commutative. So if I'm commutative, then I can take care of systems that can't guarantee the order of delivery. And if I'm idempotent, that means that I don't have to worry about the lack of a guarantee not to have once and only once delivery. So it would be really nice if I could have both. Some things in life are idempotent but not commutative. So let's take a look at HTTP again. We've got our resource with name Bob, and I'm going to put people42 name Robert, and so you would expect the name to change to Robert. Then I'm going to put people42 name Larry. And now, of course, the name changes to Larry. At the end of this, I can do my get, and I can see the name is Larry. What if I had received those two puts in the opposite order? Well, then I would get a different result at the end. When I do my final get, I would get the name Robert. So if I can see a difference between receiving the messages in one way or the other way, then my message handler is not being commutative. So my messages can't commute with one another. So that means that that maybe put, even though it's useful to be idempotent, it's maybe not giving me all the promises I need in order to build a reliable distributed system. Okay, let's see if we can take a look at this other example. We saw that scoring points in a game was commutative, but unfortunately it's not idempotent. So I've got my game where I've scored 3 points, then I've scored 5 for a total of 8. What if I find that 5-point word again and I repeat that message? I say, hey, I've scored 5 points. So now I've got a total of 13. So that might be okay for me. It's certainly not okay for my opponent. But that is not the same result as if I had only received that message once. And so that means my message handler, while it's being commutative, it's not being idempotent. So you really do want the combination of commutative and idempotent in order to take care of the two problems of distributed systems. But so far, we've only gotten through 2 of the ACID properties, ACID 2.0 properties, the commutative and idempotent properties. Let's take a look at associative. So in a lot of distributed systems, you've got nodes that perform different roles. So some will be doing your online transaction processing, so they'll receive orders and they will decrement inventory, and then they'll receive payment and they will mark accounts receivable as paid. So they are receiving all these different transactions and performing an operation on each individual one. Excuse me. And then what we want to do then is, at the end of the day, we want to see how well did we do? What was our total? And so we've got a different node sitting off to the side that's aggregating these different individual transactions and processing them in batch. So it's just receiving this entire day's batch of transactions and then running some aggregates. And then we can run our reports out of this database. And so the reports run nice and fast, and they are completely separated from the online transaction processing. So this is a great way to build a distributed application. And when we do so, we want to make sure, absolutely sure, that if our boss comes in and says, this is great, I love this daily report, I want it updated hourly, that all we need to do is change our batching schedule. And now we've got reports that still get us the same number, even though they're being batched on an hourly basis. So if we change the way in which we've grouped our transactions before we apply them to a node, we want to make sure that we still end up with the same answer. So you can see that a batch processing system needs to have the associative property. No matter where you put those parentheses, no matter where you batch things, you need to have the same result. So now we've talked about three of the properties, idempotent, commutative, and associative. And all three of these are things that you might recognize from your algebra class. And if you can find an operation that is that correctly implements these three properties, then you can build a distributed system on top of that operation. Fortunately, in mathematics, we have a name for this set of operations. And I love this name. This is where I really get to geek out, because this name really has an image that it inspires in my head. And so I want you to see it too. So these three operations taken together form a semilattice. So what we can do is kind of generalize and say that what we're talking about here is not the value, we're talking about the operation. So I will replace the operation, say I was talking about addition, we'll just call that hat. So that's the little upward pointing arrow there. So whatever operation it is you're talking about, that's hat. And then x is any value in that system. So if your operation has the property that x hat x equals x for any value of x that you could choose, then that operation is idempotent. So test that with plus. 3 plus 3, well, that's not going to be 3. So plus is not idempotent. Okay, that one doesn't qualify. But you could think of other operations that maybe do. Say greatest common factor. You know, the greatest common factor of any number with itself is itself. Okay, that is an operation that is idempotent. So if we were to think about applying new values to an existing number, what we could do is we could draw a cone. So here I'll call back to another physics reference. In physics, the set of events, the set of space-time points that could be affected by some event happening right now is called the future light cone. Basically, if you have a sphere that expands at the speed of light, that sphere now encompasses all of the future events of that one point. So if something lies outside of your future light cone, there is no way that what you do right now could ever affect it. There's just not enough time for the information to get there. Everything travels at the speed of light or slower. So this cone here represents the future light cone, if you will, of x. So anything that you could apply to x is going to be in this cone. The idempotent property says that if you try to apply x to itself, you stay right there at the point. You don't go any higher. So x hat x is going to stay at x. So now let's bring in the commutative property. So this operation that we're talking about has the property that x hat y is equal to y hat x. No matter which order you do it in, you're going to get the same result. You can visualize that by plotting the future light cone of y. So y is a value sitting parallel to x somewhere. If you were to project their possible values, whatever you apply with this operation to x is going to be somewhere in the green triangle. Whatever you apply to y is going to be somewhere in the blue triangle. Then x hat y has got to be that point where they intersect. So that means you could get there by starting at x and going up in the direction of y, or you can start at y and go up in the direction of x. No matter which way you go, you're going to get to x hat y. You could call it y hat x because you can get there from either direction. So this future cone concept gives you the commutative property as well. So now let's talk about associativity. Algebraically, we could write it as x hat y hat z is equal to x hat z hat y. Put the parentheses in either place. Visually, we could bring in z and see what happens to these future cones. So if I start at y hat z, there at the intersection between the blue and the pink, then I'll end up, when I combine in x, by moving up into x hat y hat z. Or I could have started at y hat z, or at x hat y, and applied z in order to get to the same place. I end up in the same place no matter where I started from because of the associative property. So I can put my parentheses in either place and float up into the future light cone of all of these values. So now I hope that you're starting to see the picture that I get whenever I hear the word semilattice. If you go out into your backyard, if you take a look at your roses, you might see that the vines are growing up a trellis. That trellis has a lattice shape. It's a bunch of diamonds that are all interconnected. And so the diamonds are closed at the top and they're closed at the bottom. So that's a lattice. A semilattice only needs to be closed at the top, at the bottom. It needs to be open at the top. So it's half of that shape. So you can kind of see how a semilattice it gets its name. In fact, if you dig into the research, you can see that this semilattice that I've drawn here is one type. I believe this one is called a join semilattice, and the one that's closed at the top is called a meet semilattice. I might get those terms backwards, but the important thing is that they're just semilattice, so they're open on one end. There actually is a mathematical concept called a lattice, but that is a bit too constrained for what we need to accomplish here. So, if our operation is a semilattice, that means it is idempotent, commutative, and associative, and that means that now it can help us to build distributed systems. We still have to bring in that distributed property, but this gets us a really good start. So, wouldn't it be great if I could give you an example of a thing that was idempotent, commutative, and associative? What actually is a semilattice? Well, set union. That is a perfect example of a semilattice. A set union is idempotent because if you union a set with itself, you'll get the set back itself. It's commutative. It doesn't matter which order you union the two sets, you're going to get the set back. And it's associative. It doesn't matter where you put the parentheses. Let me show you an example here. So I've got the set that contains just a car. And I'm going to union that with the set car. What's the result? It's the set car. Well, why not the set two cars? Well, that's because sets don't count things. They just contain things. So if a car is in the set, then it's in the set. It can't be in the set twice. That means that sets are idempotent. So, okay, what about commutative? If I've got the set car bicycle, or the set car, and I union the set bicycle, I'll get the result, the set car bicycle. But if I had unioned the set bicycle with the set car, I'll still get the set car bicycle. Why not the set bicycle car? Well, it's because it's the same set. Sets don't know the order in which things appear. They don't order things. They just contain things. So, is the car in the set? Yes. Is the bicycle in the set? Yes. Which comes first? Not a meaningful question. And so, set union is commutative as well as idempotent. And then associative. So I start with the set car and then I union the set bicycle train. I'm going to get the results, car bicycle train. But if I had started with the set car bicycle and then union the set train, I'll still get the set car bicycle train. So it doesn't matter how I built these sets up in the past. I could have unioned different things together in order to get different sets. Once I do the final union, I'll still get the final result, and it'll be the same result no matter where I put those parentheses. So set union is associative. Since set union is idempotent, commutative, and associative, that means it's a semilattice, which means now we can use it as the basis of building distributed systems. But we have to add one more thing in order to complete the picture, and that's the distributed property. So distributed means simply this. If I execute that transaction at any of my nodes in the distributed system, I'm going to get the same result. It seems like a pretty obvious thing that it would just always happen. I mean, why would you get a different result if you did the same thing in a different place? I mean, aren't computers supposed to be deterministic? That should mean that they always do the same thing when given the same input. But if you think about things like a relational database, if you've got an auto increment ID, then when you perform that insert statement in one place, you might get a different ID than if you perform that insert statement in another place. So that means that it's not being truly distributed. It's not giving you back the same result in every single place. It means that the ID matters. It's pinned to a location. This ID over here that happened when I inserted into the first database, that is only valid in that first database. Do an insert in a different database, that ID means something completely different. So distributed, the same exact thing no matter where you execute it. So these four properties, associative, commutative, idempotent, distributed, Pat Helland showed us that if our operation has these four properties, then it is eventually consistent. And that is a really strong statement in distributed systems, and one that has a strong mathematical definition, one that you can rely on, you can count on. And so that means you can write these proofs. You can say, this is sufficient in order to achieve that result. So now as I'm applying this, as I'm thinking through, how can I make my applications associative, commutative, idempotent, and distributed, I'm thinking not about what could I build it on top of, what database could I use that gives me ACID 2.0? No, it's not the database that gives these promises to your application. It's your application that makes these promises to your users. And if your application can provide these promises, then you can build on top of a database that doesn't provide distributed transactions. You can build upon a queue that doesn't provide once and only once delivery. You can take advantage of systems that don't have to uphold strong guarantees and are therefore probably going to be more scalable. So if you actively think about designing your applications to be ACID 2.0, then you can produce a much better, much more reliable, much more scalable distributed system. So how do you do that? Well, I'm glad you asked. Let's take a look at an example. Let's take a look at a mobile application. And this is a contact manager. So you're going to create a person inside of this application. And the application has a web API. So when the user hits that button to create that person, then it's going to post to the /people endpoint at that web API. That web API is then going to perform an insert against this database, then use identity in order to get the ID of the record that was just inserted. So it just used an auto increment ID, and it's going to get back that number. So let's say that number was 42. So now it takes that 42 and it puts that onto the URL, and it gives back this 201 created people/42. So if in the future you need to say anything about this person that you just created, there's the URL. In other words, that URL is the identity of the entity you just created. That's what you need. That's the key that you need to have in your hand in order to change that person's name, in order to look up that person's phone number, in order to send that person a private message. that is the identity that you need to do anything else in that application. And so in the meantime, the user of that application is just waiting. I mean, the very next thing that they want to do is work with that person that they just created. They don't want to create a person and then the application says, okay, bye-bye. And then they look through the list and they're not here. Oh, don't worry, they'll be here. They want to act on that record right now. So that means the application has to wait. And while the application is waiting, it's the web API that is doing the operation of let's insert into the database and then turn around and get the identity. It can't return people42 until it knows that identity. So it has to wait on the database. And so that database is there in a transaction, and it is doing that insert in an atomic and an isolated way so that other transactions that are trying to insert people records at the same time are going to get different IDs, but it'll get a unique one. And so then finally, when it finishes that and you can commit that transaction, then you've got that ID. You can create the URL. Then you can get that back to the application, and then the application can return to the user. So during this whole thing, you got the user waiting. How could we do better? Well, we can look at this operation and we can see, is this ACID 2.0? So let's take a look at some of the properties of ACID 2.0. We've got associative. Well, here we're doing only one operation, so we're not really doing an association of things here. So yeah, we'll skip associative. Commutative. If I were to create one person and then create another, I still end up with two people at the end. It doesn't matter which order I've created them. Commutative, I think we're fine. Idempotent. That's where we start to run into problems. So let's see. How is this not idempotent? So my API, I post to /people resource with name Robert. And so the API has now created that resource, and it gave me back a 201, and it said people/42, that's your identity. What if I have to repeat the message? What if I didn't hear the result? I said, hey, try again. And I send post people with name Robert. Now, since I already inserted and got people42, when I do the insert and call added identity, I'm going to get back people43. So now I have performed what I thought was one operation, but I performed it twice, and yet I ended up with two people at the end. So I ended up with a different result than if I had just performed that operation once. So same operation, just duplicated, and I get a different result. So I'm not being idempotent. Well, by a very similar token, this is also not distributed. So let's suppose that those two posts, rather than going to the same node or two different nodes that were backed by the same database, let's suppose this was going to a truly distributed system, and we have different nodes that received these two copies of the same post, and they're both backed by different databases. Now when I did the insert on this one, I got back added identity 17. And on that one, I got back added identity 351. I have just now created two different identities for the same resource. The same entity now has two different names because it didn't give me back the same identity in both of those databases. It's not being truly distributed. So this operation where I'm doing this mobile application and creating a person using a pretty standard pattern. If you were to take Visual Studio and just create a brand new web API project backed by an entity framework database, this is the pattern that it would generate. This is exactly what it would do. But it's not idempotent and it's not distributed. And so this is not going to be a good distributed systems pattern to apply. Fortunately, there's a simple solution. If post is not guaranteed to be idempotent, let's just use one of the verbs that is. Let's use put. And so put takes the full URL. The difference between post and put is that post says post to this collection and you give me back the identity. You give me back the URL. Put means put to this entire resource identifier. I'm giving you the identity. So we're going to put to /people/Bob1945. The client has chosen that identity. So maybe that's the username. Maybe that's some other natural key that the client was able to come up with. So the client puts to people Bob1945, name Robert. And now the identity of the entity is people Bob1945. If they need to put again, the identity is still people Bob1945. We're not relying upon the database to generate the identity for us. The client is providing that. And so that means that we can put again and we'll still get the same result. So this takes care of the idempotency problem. It also, as it happens, takes care of the distributed problem. If these happen to be two different databases that I ended up hitting, I would still create Bob1945 in both of them. If at some later date they needed to communicate with one another and sync up, they would say, hey, have you got Bob1945? Yes, I do. Okay, we're in sync. They wouldn't duplicate things. They wouldn't get things all out of order. They wouldn't conflict. So they are properly acting as a distributed system. Now, if you think about what this does to the user experience, it also has a great benefit there, because the user has just added a contact to their application. They've hit the submit button, and now the phone has contacted the web server in order to say, hey, put this. But you already know on the device what the identity is. Hey, it's people Bob1945. So you don't need to wait for it in order to continue working with the application. You can let the user go on their merry way. And then just in the background, you've got this process that's running in order to make sure that this gets put to the back end and you get back a successful result. Otherwise, it's going to retry. It's going to store it locally. It's going to make sure that things get queued up and sent off. But yeah, front end, the user's still using the application. So the same amount of work happening on the back end, but the user now has a much better experience. They think the application is faster. So extra bonus points for being idempotent and distributed is now the client is generating the ID, so the client can continue. So this is one good way to improve your APIs using the ACID 2.0 properties. Let's talk about messages. Let's suppose you've got a microservice. So the first service or microservices architecture, you've got lots of microservices. So the first microservice in your architecture is your online store. And what you want to do is fulfill an order that somebody has placed on this store. So they use a browser, they log into it, and they put a thing in their cart, hit submit. Boom. At that point, the online store is going to fire off a message, order placed. And that message is going to go to a topic, and you're going to have different subscribers reading from that topic. One of them is the inventory system, and it's going to say, okay, an order has been placed. I will need to pick that up. Another microservice listening at that same topic is going to see that same order placed, and that'll be the accounting service. And it'll say, okay, an order has been placed. I know that I'm going to need to charge that customer. So they're starting to do their own independent work in their own little microservices. And then the inventory system is going to look in its database and it's going to see, okay, I've got those parts in inventory. I will go ahead and reserve those and then fire off an event to a queue saying items reserved. At the other end of that queue, you've got the logistics system. And so now the logistics system knows that it can start to coordinate the picking, packing, and shipping of those reserved items. It can start talking to the people in the warehouse and saying, okay, the items on this shelf over here, directing them over there, helping them to get the right box. put it on the right truck, all that good stuff. Meanwhile, the accounting system is working on that order, and then it's going to go into its general ledger. It's going to look up the customer, the terms, and it's going to figure out exactly what kind of discounts they get, and then voila, there's the invoice. It's going to generate that invoice, put that message on a queue, and then that will get picked up by the business portal. So now the business portal is something that a different user logs in order to see how much the boss has spent on all of the widgets that he's buying. And oh goodness, he's bought another widget. Okay, I'm going to have to get out the company checkbook and pay this invoice. So that's happening on that business portal. So when they make that payment, that's another message going back on a different queue. Here's the payment. That goes back to accounting. Okay, I received the payment. Mark the accounts receivable as paid. And then, meanwhile, logistics has done their picking, packing, and shipping, and so they now have the shipment record, and they can send that to the business portal via a different queue. And now the person in the back end can log into the business portal and look to see when the boss's new widget is going to be delivered. So they've got all that shipment information. So you've got all these messages flowing through the system. And you've got queues, and you've got topics, and you've got different microservices. Some are pub sub, some are sent directly to certain microservices. Some are going in different directions, so you've got requests and responses. So you've got all this mess of things happening throughout the system. And it's your job, Mr. Developer, Mrs. Developer, to prove that no matter how these messages arrive, whether they be duplicated, out of order, associated, arrive at different nodes, you will get the same result. How are you going to do that? You have to make sure that your messages are ACID 2.0. So how do we ensure the ACID 2.0 properties of messages? Let's start with the idempotent property. So we're going to take a look at the order placed message. Is order placed idempotent? Well, let's suppose that it's represented by this JSON object here. So I've got the order ID and I've got these line items. These particular SKUs are the things that I'm ordering. So that is my order. If I see that the order is placed, if I receive that message a second time, now I can see, oh wait, there's that same order ID. I can just have a list of, these are all the orders that I know about. Is that one already in the list? Yes. Ignore it. Just drop it on the floor. The message has already been processed, and that way I can be idempotent. So, sounds like you're on the right track. Sounds like you've got a good start. But what if the web portal, the online store, is not doing things quite the right way? What if it allows somebody to add some more items to their cart and then hit submit a second time? I mean, we've all used web applications that say, don't hit submit twice. Your card might be charged twice. Bad things might happen. You might receive more than you asked for. And so you have to say, oh, okay, it's spinning. Did it make it? I don't know if it made it. Yeah, it's been 30 seconds. Maybe I should hit submit twice. Nope, I shouldn't. I really shouldn't. And so these applications are not being idempotent with their messages. But what if you have an application that's poorly designed and it happens to send a new order placed message with the same order ID, but now more line items? You've allowed the user to add more stuff to their cart, hit submit a second time, and now you've got this duplicate order, but it's different than the others. What do you do? Well, if you had received the first one, then when you receive the second one, you'll say, oh, same order ID, drop it on the floor. They'll get their ABC and their DEF, but not their GHI, JKL, or MNO. So you have to instead actually handle that message. But maybe the first one was correct. I mean, so what do? You have to be idempotent, but the message has changed, or rather the order has changed. So what you want to do really is to enforce not just idempotent messages. You want to enforce immutable messages. You want to make sure that messages cannot change. So that seems like a pretty tall order in a distributed system, where you have to say, well, okay, if you send me another message, but it's got the same order ID, then you have to use the same line items. Otherwise things are going to break. How are you going to enforce that rule? Fortunately, there is a nice way that we could do that. What I have here is this order.json. It's just this this JavaScript file. It looks exactly like the order that we were talking about there. In fact, let me go ahead and pipe that through JQ so we can see it nice and pretty. I'm going to squish that down into a single line. So I've stripped out all of the white space. And let's suppose that that I could do this with JQ. I can't, but it happened to be such that let's suppose that I can put all of the fields of this JSON object in alphabetical order. Now, what you would say is that anybody who took the same message and did those operations, remove white space, put things in alphabetical order, they're going to get the same message. So you've got this canonical form of the message. Okay, so I'm going to take this canonical form and I'm going to pass it into a little hash function, compute the digest, and I'll use a SHA-256. That'll be big enough. So that's going to give me some binary, so I'm going to run that through base64 to encode that binary, so now we can see what that looks like. So that string right there is a digest of that message. Moreover, it's a digest of the canonical form of that message. So if somebody else were to send you that message and you ran through these operations, you would come up with that same string. So what if the order ID wasn't the unique identifier of this message? That's just the unique identifier of the order. This message is identified by that hash. So now you've got a way that you can enforce the fact that your messages are immutable, because if you change this message, you're going to get a new hash. So that means that now you can look up, not by order ID, but by message ID, have you processed this message before? And if so, you can drop it on the floor. You know that everything inside the message is exactly the same as what you processed in the past. But only if that message ID is different is this a new message, and you can handle it. And that way you can be immutable in all your message processing. So that one simple addition to all of your handlers makes them immutable. Keep track of the messages that you received by their hash of the canonical form, and then just ignore those that you've already processed. So that buys us the idempotency. Now let's see what we have to do in order to be commutative. So these were the 5 different types of messages that we saw flowing through the system before. So we've got that the order was placed, items were received or reserved. We've got the invoice being generated by the accounting system, payment coming back to the accounting system, shipment going to the portal. So these are the different messages that are flowing through the system. And I want to make sure that they all commute with each other. So that means I need to compare order placed with items reserved and see, will I get the same result if I commute those? And then, let's say that, okay, I can't reserve the items until I've placed the order, so let's go ahead and hold the reserved items until I see the order placed, and then I'll process them both. All right, we can handle that one. Now let's compare order placed with invoice. Can I handle those in the opposite order? Then items reserved with invoice, and then items reserved with payments. And now you get this combination of all the different messages. Can they commute with every other message? And it just becomes a nightmare to keep track of things. Every time you add a new message to your system, You now have to compare it with all of the others to see if it commutes with everything else. And that is just insurmountable. This is a simple example, and we already have 5 messages, which means that we've got 5 times 4 divided by 2. We've got 50 combination, 50 pairs of, wait, no, that would just be 10. Yeah. I didn't say that I was really good at multiplication. But you've got these 10 pairs of messages that you need to commute. So what are you going to do? How are you going to make sure that these commute? What I would say is don't look at it just as individual messages like this. Let's just rearrange things. And let's look at it like this. What I've drawn here is an arrow if the message at the tail of the arrow comes after the one at the head of the arrow. So you place an order, and then you can reserve the items. You can't reserve the items until the order's been placed. So order placed is a prerequisite. It must have happened first. So I like to use the term predecessor for those kind of messages. The opposite dependency there is successor. So order placed, one of the successors is that you can reserve items. So placing an order now allows you to write an invoice. You must place the order before you can create the invoice. So order placed is the predecessor, invoice is the successor. So you can evaluate the predecessor-successor relationships of the different messages, see what has to happen before what else. And you'll notice that you don't end up with a strictly linear, this has to happen, then this, then this, then this chain of events. You end up with this graph. You end up with a partially ordered graph of events where items reserved can happen before or after the invoice. Items reserved is over here on the inventory system, and invoice is happening over here on the accounting system. And the accounting system isn't going to wait for the items to be reserved before creating the invoice, and nor are we going to wait for the invoice to be created before we reserve the items. Those things can happen in parallel. And so there's no causal relationship between the two. Neither one has to happen before the other. And so if you build this graph, now you can think just about where the arrows are. So instead of all 10 pairs of different things that are happening here, you just have these 4 arrows, these 4 causal relationships. And that's because when you're talking about commutative messages, what you really want to think about is partially ordered messages. So this is where I'm going to call back to mathematics again. So in mathematics, some sets are fully ordered, like the set of integers. 1, 2, 3, 4, 5. You know the order in which they happen. Take any 2 integers, you know that one's going to come before the other. And you can use a little operator called less than in order to tell you which direction they happen in. In a partially ordered set, some things might not happen before or after other things. You might be able to pick 2 items out of that set, compare them, and hey, they can happen in either order. Kind of hard to think through what an example might be, so let me give you one. Well, let's suppose that we are talking about factors of an integer. So here we can say that 14 has a couple of factors, 7 and 2. So 7 is a factor of 14, 2 is a factor of 14. We can say, in that sense, is a factor of, puts 7 before 14, puts 2 before 14. But neither 7 nor 2 is a factor of each other. They're partially ordered. They could be in either order, and it doesn't matter. So if you were to apply that partial order to your messages, now you get this thing where things can happen in different orders, and it's okay. We don't have to worry about those things commuting because they're not related. So how can I ensure that I follow the commutative property if now I've got this partially ordered collection of messages? So I can ignore those that don't have a relationship with one another. That makes things easier. Now, when things do have a relationship, how can I make sure they commute? My favorite technique is to just embed your predecessors. So remember, the order was the predecessor of the invoice. So that means that the order has to happen before the invoice. The invoice doesn't make sense without the order. And you can kind of see that when you take a look at the handler. You receive an invoice. What's the first thing it's going to do? It's going to look up the order so that it knows what items are in that order, so it can compute the cost and put that on the invoice. So it needs that information anyway. That's a predecessor. It has to have happened first. So why not just embed it within the message? So that helps you because now if you receive the invoice before you received the order, you can just look inside the invoice and say, oh, there's the order. Let me go ahead and process that first. All right, now that's done. Now I can process the invoice. You've received this invoice out of order. You received it before the order, but you can still go ahead and process it. It's okay because it contains its predecessor. So just embedding the predecessor means that now you can commute across those arrows, across those causal relationships. Now, there are alternatives to doing this. Of course, you could, instead of having the actual order there, you could have the message ID of the order. And then you will know that if you receive this, you can look up that message ID, have I received that before? And that gives you the order indirectly. But then if you haven't received that order, you can't process it out of order. You can't commute. You just have to put the invoice aside and wait for the order to show up. And then check your queue over here. What have I put aside? Oh, here's an invoice that depends on it. Pull it back in. That's an algorithm called a topological sort, which I definitely recommend that everyone try as a kata, but it's a little bit tricky to implement. So even though that might save you some space in your messages, it can be kind of a difficult algorithm to maintain. So it's definitely easier to embed your predecessors, even though it might take up a little bit of extra space. So now you've got messages that commute, messages that are idempotent, and now we can quickly talk about the other properties. So the associative property. What do you do with these messages once you receive them? Well, if the thing that you do with these messages is you put them into a set, now you're performing a set union. Here's a message, union it with the set. Set might get bigger if I haven't seen it before, or it might stay the same if I already have. Set union, we already saw, is a semilattice, and so we can get to the associative property out of doing that set union. So now if I just have this database where I don't update orders, I don't update invoices, and I certainly don't delete anything, I'm just inserting. And I'm only inserting if that identity is unique. Now I have just created an insert-only database, a database that is a set union, and I am ensuring that I'm associative, commutative, and idempotent. So that is the way that I really like to build my systems, is just insert, never update, never delete. And you can get those systems, those promises, because it's a set union. And then distributed. Well, if that's the ID, everybody's going to compute that same ID. That's the same identity no matter what system handles it. So that means that the handler can be distributed as well. It can do the same thing. It can generate the same identity no matter where you are. You're not relying upon a database to increment a value. You're using that as the identity everywhere. So these techniques give you the ACID 2.0 properties of messages. Now, it does lead to some differences in the way that you have to think through things. Now, I said that with these kinds of databases, you only insert, you never update, you never delete. So what if you do need to update a thing? So let's suppose that the user is looking at their page, they've added things to their cart, and they hit submit. And now they really do need to go back to that cart and change something. They need to add a new item to it. They need to take something out. They need to change the quantity. They need to use one product versus another. Somehow they need to change their order. If we have disallowed updates in our database, we've disallowed modification, mutation of our messages, how can we update? The way that we would update is that we would create a new message, and we would use the old one as a predecessor. So now it's not just, hey, this order was placed. Hey, this other order is placed. And you've got these two orders that are not related to each other, and they could happen in either order. Nope, you've got this order was placed. Hey, this order replaced that one. That one is a predecessor. And so that means that you've embedded that predecessor in the order that's replacing it. That means that when you receive it, you know that this one supersedes its predecessor. And so now you know that the one at the leaf of the tree, the one at the bottom of that chain, that is the most recent one. And you can process that order. So that takes care of updates. What about deletes? Can't delete an order. What if the user actually does want to go over there and hit cancel? Well then, we've got an order canceled event, and that comes that flows in through the system. And it's not flowing in independently. It's not saying, hey, an order was canceled. It's saying that order was canceled. So it uses the order that it's canceling as the predecessor. It tells you which one. And so that means that if you receive this message, this whole aggregate of this order was placed, hey, then it was changed. It was replaced with this version of the order, and then the whole thing was canceled. If you receive that and you say, well, I hadn't processed either of these two. Oh, it was canceled. Okay, fine. I'm not going to do anything. But the problem with a lot of systems is, you've placed the order. You sent that off. You want to cancel. You can't pull the order back. It might have gotten processed. So you just have to go forward. So if it already has gotten processed and you receive this structure here, you can see that. You can see, oh, this order was placed, it was changed, and then it was canceled. I already processed the first one. Okay, I know what I need to do. I need to remove the reservations on these items because I'm the inventory system. Okay, great. The accounting system receives this structure and it says, oh, I've already created an invoice for this second order. So all I have to do is reverse that invoice. You never delete anything in an accounting system. Don't delete your invoices. Accountants don't use erasers. They go to jail. But it can reverse that invoice. It can insert another record into the general ledger that takes that back. And by the way, the reason that accountants don't use erasers is because they're following a system very much like this. They have immutable records. And that is how they keep track of history. That's how they model the history of their applications. So this is how I like to approach message design in order to make sure that my messages are ACID 2.0. So if I'm making my web APIs ACID 2.0, I'm making my messages ACID 2.0, that means that I am providing promises to my users that when they batch things up and they send a bunch of information to me, my application is going to be associative. It's always going to come up with the same result as if you'd have batched it in a different way. If you get things out of order, my application will be commutative. I can handle those out of order messages. If you send me the same message twice, that's okay. My application is idempotent. It's not going to duplicate the effect just because we duplicated the message. And my application is distributed. No matter which node you happen to be talking to, it's going to give you the same result. And that way, when all the nodes talk to each other, they will be eventually consistent. It will always converge to the same state. And it'll be a state that makes sense because it's all derived from this partially ordered graph of immutable objects. So I go through all of this in greater detail in a new book, which I've finished writing and is just about to be published in about a month. So if you go to immutablearchitecture.com You can sign up for my newsletter. I will let you know the moment that the Art of Immutable Architecture is available for you to purchase and download on your e-reader, and start to learn all of the ways in which your applications can be a better, more reliable distributed system. Thank you very much.
Awesome. So anyone have any questions?
Certainly couldn't have explained it that well.
Burger servers, everyone's still trying to sink it all in, right? That was definitely a lot.
Yes, indeed. Yeah, I've been, like I said, researching and reading math papers for quite some time to assemble all this. So it does take time to soak it all in. But yeah, what I found is the patterns that we are taught to use don't take these properties into account. And so, like you use Visual Studio template to create a new project, you're going to get something that is not idempotent. You're going to get something that's not distributed. And you don't know at that time what problems it might cause for you in the future. So I think it's important to learn these concepts and learn how they all fit together.
You might be having a question coming in from Twitch, but someone said they have a question, then they haven't asked the question yet. Oh, okay, here we go. I'll just paste this over to that chat. So that just came in from Twitch.
Alrighty. Love the light cone. Awesome. Yes. So if the idea is to embed, but we can receive messages out of order, then how do you handle when the first message comes in after the delete message? Okay, good one. So yeah, the delete message, since it uses the order, the thing that it's deleting, as a predecessor, that means delete embeds the thing that it's deleting. So so what you would do is you would receive that delete message. You would see, okay, have I actually seen this message that's inside of it? And if so, now I know I have work to do. I can go ahead and delete that object. But if not, then I know that I can optimize. I can say, well, I don't need to actually create that thing, but I do need to save this message here that I've seen it. So I've seen the order and I've seen the deletion. So now when the order comes in, it says, oh, I've already seen it, drop it on the floor. So that same idempotency check is now making sure that my deletion doesn't get undone when things arrive out of order.
Fair enough. So John, let me know if that answers your full question. Oh yeah, he says thanks.
Cool. Yeah, and taking this to the extreme, there's a way that I really love to account for this, and that is that that when I receive something like a deletion, I'm just going to insert a new record into the database, and it's going to have, I'm going to represent my predecessor relationships as foreign keys in the database. I'm not using those IDs outside of the database, but it's okay to use them inside the database as foreign key references. But now I can run a query when I'm looking for all of my orders. All I do is I say select star from order. Well, don't select star, but you know what I mean. Select star from order where not exists. Select from order ID, or from order deleted, where this order ID. So you have this where not exist clause in your query. And so now inserting a delete record into a different table, this deletion table, causes that query to no longer return the order. So you haven't actually deleted the order from the database, but you have effectively removed it from the results. So that's like the extreme way of doing the same thing. But the advantage there is you've got that full history now. One of the things that one of the challenges that I hear an awful lot to this style of development is you're never deleting anything. Doesn't your database just grow unbounded? Well, let's think about the value of the data that you're inserting there. Let's suppose that you're taking these orders, and you're inserting them into the database, isn't it valuable to your marketing team to know the history of orders, not just your current accounts receivable and your current inventory, but what have people ordered in the past? Now they can do analytics on that, and they can see, these things were ordered together. They can build value into the system, and that value comes from that history. That history is valuable. So yeah, even though we originally were doing this to solve distributed systems problems, hey, just go ahead and use an insert-only database. Just collect information. Just use these where not exists clauses, and now you are retaining all of that valuable history. And go up to any cloud provider. Compute is going to be expensive, but storage is going to be cheap. So
To a point.
Go ahead and pay that money to get that valuable data.
To a point.
Yeah.
I'm actually dealing with we've got a database that's getting ready to hit a terabyte, and once it does, our cost is going to go up quite a bit. So, which is why we're working on some archival strategies.
Yeah. But you're archiving. You're not just deleting data, because that data is valuable. It's just not going to be updated very frequently anymore. So let's carve off the data that's not going to be updated frequently, put that into a colder storage where we can read from it. We can do our analytics, but yeah, it's not going to be quite as expensive.
And there's a comment on Twitch that I've always said that deletes are bad.
Yes. Yes, deletes are bad. I remember the first time that I learned this was way back when. Does anybody remember Windows Mobile? I had a device. I think I might even still have it somewhere around here, called a Cassiopeia. It was the first PDA. Basically, well, not the first PDA, but my first PDA. But it was a Windows Mobile device. It had this really blocky black LCD touchscreen, and so you had this big old start button in the bottom. This was it was Windows 95-ish running on this thing. Hit that start button, things pop up. Hey, I can get into Outlook. I can store my contacts. Well, this thing also had a dock that you popped it into. That dock had a serial cable. This was before USB. A serial cable that plugged into the back of your machine. And then Outlook would pop up on your machine, and it would sync things up. Well, this thing had this really bad habit of, I deleted this contact from the device. And then over here, I happen to have received a new email address from that person, so change their email. Okay, pop, sync. Outlook says, oh, wait a minute. You're trying to delete here, but you're trying to change it here. So I don't know what to do. I'm just going to recreate that object on your device with the new email address. And it's like, what did you do? I was trying to delete. They since fixed that by doing things called tombstones. This was ActiveX sync or ActiveSync. And so they created these tombstone objects that said, this thing is deleted, but the thing is still there. It's just a tombstone that rides along with it. And so they learned that deletes are bad. And then they just keep track of the tombstones. And now things don't get out of sync like that. There aren't any conflicts in that same way.
So you do have another question in the chat.
Mm-hmm. Yes. So not sure you have time now or here, but would be nice to explain in detail the different ways to store these messages with advantages and disadvantages, including table structures and fields. Yes. Okay. This is a great one, because the way that I like to do this, it depends on how I'm going to be using this data, but oftentimes you'll find that when you are storing things as immutable graphs of these records, you're going to be querying them based on their relationships, not based on their fields. So storing these things in a relational database where each of these fields is a column that is putting it into one shape that you're not going to take advantage of. And then you have to take it back out of that shape and put it back into this shape. So I'm not going to be looking up this object by order ID. So I don't need an order ID column. I'm going to be looking it up by that identifier there. So that means that I just really need to have, if I am using a relational database, a table that has this as the primary key, and then that as the only value. Well, now you're not really using a relational database for what it's really good for. Why not store that in a NoSQL database? Why not store that in a graph database? It opens up these other options for you. And now it gives you the opportunity to query this thing according to their relationships and not according to their individual values. Here you see a couple of relationships hidden inside of the structure. If I were to take a look at the invoice, you can see this one. I have embedded the order. There's the order embedded within the invoice. So, so putting that into a relational structure, you're not really getting the benefits of the relational database. But if you have the invoice, which has this information, but then replace the order object with just that foreign key. Now you've got the way that I like to think about it is you've got a table that stores just the fields, like you've got the invoice ID is one of the fields, and then you've got another table that stores your relationships, where this invoice, which is, if I were to run it through this, would get a different identifier. This identifier is related to the order, which has this identifier. So that's now a relationship table. You can join on those tables. You can find all of the, you can find the invoice for this, the invoice for this order using that join. And now you can run that query to say, has this order been invoiced? That now gives you a direct query to check the status of the order. And so you don't have to worry about updating a status column. That's out of your data store. You just, does the invoice exist? Okay, it's been invoiced. Does the shipment exist? Okay, it's been shipped. And you can answer those questions directly against that database. It's a database that focuses on the relationships, not on the columns. So, long answer for your data storage mechanism is open to you. You've got all these different possibilities. If you end up using relational, you're not going to be using relational for what it's really good at in this structure. Relational is really great for doing running reports for business intelligence, for those sorts of things. Running a report out of this data structure, not going to be happy. You're not going to like it. So you take this structure, then you transform it into your relational database in order to get your static view of the data. Run your reports out of that system. It's separate from your transaction processing system, and then you'll be in a much happier place.